Okay, so let's write what we found out. Let me go to another. There we go. Okay, now the first group, this group right here, what did you pick as far as a card or a suit? What did you pick? Okay, the probability of an ace. Okay, what number did you pick on your die?
3.
Probability of a 3 on a die. Okay, now the theoretical probability of an ace, I don't know how to spell theoretical, so, okay, thank you. I don't know if it's even right or not. What? Theoretical is it right or not? Well, somebody look it up. Theoretical is 4 aces out of what? And somebody do that on your calculator. What's 4 out of 52? Somebody give me a decimal. 2 decimal places. Okay, and 3 out of 6. Or, I'm sorry, it's 1 out of 6. Now we done changed from eraser to green marker. I don't know how I did it, but that's 1 out of 6, which is equal to 0.16. Now, the physical probability, anybody check my spelling? Okay, so no H. Right here. Okay, there. All right, physical probability, my perfection is off today. I'm sorry.
That's okay.
All right, I'm excited. I hadn't walked on water in a while. I'm sorry, y'all. Let's go with how many times did you get an ace in your group? 1 out of 20, which is equal to divide by 10 over 10, or divide by 2 over 2, which is 0.05. And how many 3s did you get? 5 out of 20, which is equal to 0.25. Well, they don't match up. This doesn't match up either. Group 2. What did you pick for your card? A queen. So again, that's 4 out of 52, which is equal to 0.07. What? Hey, thank you for leading me astray. Thank you for telling me wrong. You're going to fail. And what was your number?
6.
And again, that would be 1 out of 6, which is equal to 1.6. I'm not going to worry about it right now. Like I said, I quit walking on water a long time ago. All right. So, oh gosh, I referred to something in the Bible. Oh God. Oh God, I said God. All right. Now, what's your actual? I'm gonna protest. What's your actual physical group 2 on the queen? 1 out of 20, which is equal to 0.05. They're not equal. What's your, on the number, what did you get?
7.
7 out of 20, which is equal to 3.5.035. Y'all check me.
Yes.
All right. Now.
Oh, 0.35.
Oh, it's not 0.035? It's not. Oh, I moved it to the calculator. That's all. Let me change this real quick. Okay, group 3. Group 3. What did you pick, Mr. Harvale? You picked the 3 out of the cards. And what number on the die? 3. Okay, that's pretty consistent. So that'd be 4 out of 52 and 1 out of 6, which is equal to 0.08. Oh, y'all are just a wild bunch, let me tell you. So unpredictable. 1.7, 1.7. And what did you actually get on your 3 of cards? 1 out of 20, which is 0.05. And what did you get on your 3? 3 out of 20, which is, thank you, 0.15. Again, they don't equal. Now some may say, oh, well, they're close, yet they're not equal. Because there's this thing in statistics and probability called the large number rule. The more events / tries / observations, whatever you want to call them, the closer you get, the closer the theoretical probability equals the physical probability. Now, there was a study done, in fact, in Triola's book, in Math 120 book, there was a couple of students in a university, probably somewhere like MIT or somewhere, and they wrote a computer program, and what they did is they took several rolls of quarters, and let's say 3 rolls of quarters. How many quarters are in a roll? I don't know.
$10.
$10. There'd be what, 40? All right. So they took 120 quarters. Now, of course, they may have done 20. I just picked 3. And they measured the weight, the circumference, or whatever you want to call it, the circumference, the diameter, the width, and they measured all of this stuff. And then they took an average. They took an average and they took out any outliers. It may have been a defective quarter or whatever. They threw it out. They might have been a quarter that was cut in 2 or a piece of it cut out. They threw it out. All of the weights and circumferences and diameters and widths that were close, they kept. And then they took an average and they got 1 quarter that represented, they got 1 quarter by weights and measures that represented all 120 quarters or however many quarters they measured. And then they took that information and they wrote an algorithm or a computer program. I don't know how to spell algorithm, but anyway, an algorithm or a computer program. And then they figured the computer program to flip computer generated flips. Computer generated flips. And what they found out is, what is the probability of flipping or getting the tails or heads or flipping a coin? 0.5 or 1/2. That's the theoretical probability. Well, they flipped it 10 times and they found out it would be 0.7. They flipped it 100 times and they found out it would be 0.15 or whatever the case may be. What number, how many flips did it take the computer to get the theoretical probability equal to the physical probability? Well, it took close to 100,000 flips, and the physical probability came out to be 0.4999995. Okay, 100,000 flips for the physical probability to equal the theoretical probability of 0.5. Now, what the heck does this have to do with statistics and probability? Well, I'm just gonna job security. Why would it have anything to do with job security? Well, let's say that you're a director, executive director with Michelin. And let's say that you work in the Crystal Palace up there in Greenville, right between Greenville and Spartanburg, that big old. So you don't come home with black all over your face. So you come home every day in your suit and tie or your suit dress or whatever, and you make 5 or 6 figures up there, and you go to these plants in Sandy Springs and over here on 29, and you just say, hey, how y'all doing? I'm here. But the people from France come over and you have to give a presentation. And that presentation every year is the builder for the budget for the next year. And your job is quality assurance. You go to the Sandy Spring plant and ask them to pull 10 tires, and go down here to the 29 South and ask them to pull 10 tires, or do you ask the Sandy Spring, and they call it Star plant, but it's really not Star. But anyway, it's LA is what it is, but they want to give the money to Crescent, so that's why they put it in Star. But anyway, the whole point is, do you ask for 10 tires from each plant, or do you ask for 1,000 tires from each plant? 1,000. Why? Because the next year's budget depends on what you and the other department heads or directors have to say. And if you go in there with 10 from Sandy Springs and 10 from Star, and you say, well, looks like we only gonna have 5,000 bad tires next year. Okay, put that in the budget, 5,000 bad tires, and it comes out to be 50,000 bad tires. What are you? Fired. And then you have to protest because you got fired, and you feel bad about yourself. Probability, surveys, statistics, observations, experiments, if your reputation is going down on it, then you need to make sure you get plenty of observations or plenty of experiments or plenty of numbers to back up what you say. And that's true with anything. You don't want to, in fact, like let's say you work at, let's say you're a nurse, you're head of nursing at blah, 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 blah. And you're supposed to give a synopsis on how the mortality rate on your floor is. And whether it's the old people's floor or the heart floor or ICU or whatever the case may be, you're supposed to give that. Well, you want to make sure you don't just say for 2017, you want to look at 2017 and you want to go at least 5 or 6 years back to see if you are crappy nurses or to see if you are pretty good nurses. Now, people are going to die, but you have to back that up. You can't just throw numbers up and say, okay, here they are. Y'all decide what y'all want to decide. You'll get fired. Now, what if you're never ever going to do a presentation in your life? Well, the knowledge is here that person, hopefully, that's presenting to you has got the numbers to back it up. And that's the first thing you're going to ask. Now, what do they usually give you when they give you this? N is equal to what? Some number. And that number needs to be a DA number. Okay? If you're giving a presentation on tires, you want those tires at least 1,000 that you pulled, not 10. And usually with any kind of statistics or any kind of probability, you'll see this somewhere on the chart, on the graphics. You're going to see it somewhere. And it's going to say N is equal to 365,000 people surveyed or something like that. The bigger the number, the better the doubt. Okay, so that's why we have the big number theory. We don't have the big number theory or the large number theory just to have it. We have it to back up the numbers in statistics and probability. Now, something else that you need to know about probability. You need to know how to read. Because the problem in statistics is not the math. It's the what? The wording. Later on, we're going to see a difference between the word is and between the word or. All depends on what your definition of is. Who said that? Bill. I did not have sexual relations with that woman. Okay, is or. You're going to have to look for that in a sentence. You're going to have to look for the words odd. You're going to have to look for the words even. You're going to have to read the question. Okay? It's going to ask you what is the probability that that you get the probability of an even card in the deck of cards. Well, right then you've got to think. Okay, there's 2, 4, 6, 8, 10, and then what else is even? No, 12 is not in the deck of cards. The ace is not even. It's an 11 or a what? There's king, queen, and what? Jack. So that's all the even cards in the deck of cards, but you got to multiply it by 4. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is what? 32 over what? 52. So just this one word changed your whole outcome of your question. You've got to read the question. All right? Well, here's another one. This one get on test. Probability of rolling a 7 on a die. Huh? You know, people miss that question. They'll put 1/6. Why is it not 1/6? Because it's not a 7 on the freaking die. You got to read the question. And whenever you're dealing with some of these questions, you got to read it. One question they ask is well, I'll go ahead and show it to you. I done forgot the problem. Forgot the thing. Roulette wheel. The roulette wheel. I doubt I can find one. Let me just Google it because they don't have one in this book because I think y'all too stupid to do it. So let me just pull it up and Triola. That. Let me see here. Well, thought it would be. There it is. All right, read that question and write it down. I want you to write all 3 of these down. A, B, and C. Because this is one of those questions, this is one of the best questions that's been in a book where you have to read the question because some of you won't read the question right. A roulette wheel has 38 slots. One slot is 0, another is double 0, and the other is a number 1 through 36. You place a bet that the outcome is an odd number. What? Is that good?
Now, the part about I want you to understand is you place a bet that the outcome is an odd number. Now, I'm not worried about the B and C. We'll do that when y'all come back, because we're about out of time right now. And I want to get out early so I can do my video before Mr. Newton gets here, so we'll go ahead and let y'all go after this one.
Probability of success or probability of winning would be an odd number, right? What would the probability of failure be? Good. Not odd would be two more than what you got. If you say even, then you're both going to come out with the same numbers. And that's where people get this problem wrong. They got to read the question and the complement of odd is not odd. Here, what's half of 36? 18? 18 over 38. And what is failure? 20 over 38. And that's where people get it wrong right there. They say 18 over 28 for both, 18 over 38 for both. And that is a prime example of people not reading the question and then thinking too much. Okay? All right, y'all get out of here. Have a good day. I'll put some homework up on probability, but that's about it. I won't put anything else up. Oh yeah, put the cards in the die up here. Thank you.